Yeah.
I also want to continue.
But I also want to learn.
I know. Okay, so you just turn it on right now.
Yeah.
And I turn it off. Okay, let's see. I thought I was turning it on. Okay, great. So we are back. So what is left is to do this same thing for a charge outside. And okay, so what happens? Now you have a surface, and then let's say that you put the charge outside. And I'm walking around that surface like before. Okay? So both those patches that I just built are going to have the same contribution on the sphere, right? I'm going to see them the same way. But now, so over here, the electric field is going to be like that, and the patch of surface is going to be this way. Okay, so the two contributions here are basically going to cancel each other out. Okay, and then basically, if you consider a cone that is tangent to the object, to the surface of consideration, then there's going to be a bunch of contributions that are going to be positive and a bunch of contributions that are negative, and that's going to cancel out. Okay? So the point then is that if we have a charge outside of the surface, it's not going to contribute to the integral E dot ds. So now the conclusion is the following. In general, we have, like I told you before, maybe 1 million charges that are generating an electric field. So the 1 million charges are fixed in space, and the electric field is also fixed in space. Now we place some surface that is arbitrary. When we place that surface that is arbitrary, some of the charges are going to lie outside of the surface and some inside. Now, the field at one point on the surface is going to be a superposition of all the charges. So clearly, when we do this integral, if the charges are inside of the surface, they are going to contribute to terms like this type, Q over epsilon 0. So we're going to have Q1, Q2, Q3, whatever, all the charges are inside. And then the ones that are outside are not going to contribute. Okay, so then we can generalize this result to say the statement of the Gauss's law is that whenever we do the integral on a surface of the electric field on the surface, we are going to get the total charge inside divided by epsilon 0. Now, this is interesting because you have to remember that the charges, all the charges that produce the electric field, all the charges produce the electric field, whether they are inside or outside. It is only regarding the Gauss's law that the outside charges don't matter. They do affect the way the electric field is produced. That's for sure. It doesn't affect Gauss's theorem, the ones outside. Okay? So now that we have this, let's get this interesting result. So a few classes ago, we proved the divergence theorem, if you remember. So what was the statement of the divergence theorem?
The line integral to the surface integral?
That's, well, no. The line and surface is talks and it's a little bit different. But what was the divergence theorem? The divergence theorem connected a surface integral with a volume integral.
Yeah.
And it's called the divergence theorem. So,
It's the surface integral is equal to the volume integral of the divergence.
okay, great. So that, we proved it before, so now we're going to use it, okay? So for example, I have here in Gauss's statement that thing, okay? So I want to consider the same integral that appears in Gauss' statement. So I take a surface and I just write the right-hand side of Gauss's, okay? And according to the divergence theorem, this is equal to the integral in the volume of the divergence of the electric field integrated in the volume. What do I do here? I don't want to use V, the electrostatic potential, okay? Or I use before the R or whatever, okay? I don't want to use the letter V like that because it's the electrostatic potential. Okay, so, all right, now let's consider, so the picture is that we have a surface, like in Gauss's before, and in the things that we did before, and then inside that surface we have a volume V. Okay, so now let's say that this charge Q, okay, in general, is going to be given by a certain density. Okay, for example, the charge we learned before can be distributed on surfaces, on lines, on volumes, or could be points, okay? But let's say, just to say it very quickly, that if I have a point charge, nobody will complain to say that there is a highly concentrated amount of charge with a volume density rho on a very tiny sphere. Same, right? It's the same thing, okay? As long as we don't look too close, it will be the same thing. Okay? It can be formalized, but I don't care about that for now. This is good enough. So the point is that whether we have point charges that can be considered to be very tiny spheres, or we have lines of charge that can be considered three-dimensional wires, or we have surfaces that in reality are three-dimensional objects, doesn't really matter where the charges are. Now I prefer to look at all the charges from the perspective of three-dimensional densities, okay? And we call those rho's, remember? Okay, so then, doesn't really matter where the charges are in three-dimensional space. I can characterize the distribution of charges by charge density rho in 3 dimensions, formally at least, okay? And so that means that the Q can be written as the integral of rho dV in the volume V. In other words, going back to this picture, if I have a surface S in Gauss's law and in the divergence theorem, I can represent formally all the charges inside. Now imagine that all this region inside is covered with charges, and outside also, but the only charges that matter for Gauss's law are the charges inside. For that reason, when I do the integral of the charge, I don't go to the full three-dimensional space, I only integrate in the volume. So I make this claim that this is true. Well, I'm just explaining why that's true. Okay, given a charge density rho in three-dimensional space, out of that rho, the only charge that is going to be inside the volume is the integral inside that volume of rho. The rho that is outside doesn't. The rho that is outside that generates charge doesn't matter for Gauss's law. Okay, very, very good. So with that, with those two, so with the divergence theorem and this realization, now I can write Gauss's law again. But instead of using the EDS, I'm going to use this part of the divergence theorem. And instead of using Q inside, I'm going to write this new thing. Okay? So Gauss's law now reads like this: 1 over epsilon 0, integral inside the volume of the density dV equals the integral in the volume, and this should be that V, of the divergence of E times the element of volume. Okay? So that thing is a completely equivalent statement of Gauss's law, but now in terms of the density, not the charges. Okay, so since, as I told you, I emphasized that this surface S in Gauss's law is absolutely anything that I want, could be any surface whatsoever, I am going to consider out of all those infinite possibilities one very interesting case. Let's suppose that I take a surface that is very, very tiny. Okay, so meaning that the volume contained in that surface is very, very tiny. Since this result is true for any surface, it's going to be in particular true for a tiny surface, a tiny volume, correct? Okay, so take V small, and the justification for that is because we can, because it's still true, okay? But if the volume is small, then the integrals become very simple. Because if I have a density, okay, throughout space, but now I'm integrating a very tiny volume, this integral becomes nothing but the density at that location of the volume times the dV. Well, no, it's Q, sure, but I don't want to go there yet. Okay, so if I have a volume that is 1 micron cube, all I do is I just, to do that integral, is I take the density at that location times the volume for that integral, okay? Fine. So then, for small volumes, I can write this, that 1 over epsilon 0 times the density, and now I'm going to emphasize that that density, that in general varies from point to point, now I'm going to evaluate it at the location of the volume. So we still have 2 minutes to go, and I will finish. Yeah, no, this is important. So, and then same thing I can argue for the right-hand side, and it's the divergence of E. And now I want to emphasize that that divergence is taken at the point R where the volume, the tiny volume was, times dV. Okay, this volume is small, the volume is small, so it doesn't matter. Okay, at the so-called differential form of Gauss's law. And I will write one more thing before we finish the class. So what we just learned is that the divergence of E equals 1 over epsilon 0 times rho of R. Okay, so this is an amazing statement because this is a local statement that tells me that the divergence of the electric field at one point in space depends only on the density at that same location. Doesn't really matter what happens far away. Okay, the divergence depends only on what happens at that point. And so the only one more thing that I want to say before I let you go is that because we are going to really learn a lot from that. This is something that is going to be the beginning of a different way to look at everything, or problems in electrostatics. We learned before that the electric field can be obtained from the electrostatic potential that way. And so now we can put this electric field into this equation to obtain that the divergence of the gradient of the potential at location R is equal to minus 1 over epsilon 0 times rho at location R. But these two guys together is a Laplacian, okay, that has, for example, in Cartesian coordinates, the gradient, the divergence of the gradient is going to be the second derivative with respect to x, plus the second derivative with respect to y, plus etc. Okay, so this guy has a special name called the Laplacian. And it's so important that even has a special symbol, of course, that squared, okay? Some people also use this one, but we are not going to use it, okay? So just tell you. So this in compact form can be written as And okay, I'm gonna finish here, but this is called Poisson's equation. Okay, and this actually, if you think about it, we haven't done too much, but learn Coulomb's law. There is nothing else in everything that we've said, nothing else. So this is really Coulomb's law. Okay, except that now we have a differential equation because we have derivatives on v equals to a function, okay? And so this will allow us to look at the electrostatic problems from a different perspective and solve situations that wouldn't be possible if we only need to know where the charges are. Okay, so
Is it the volume or the voltage?
yeah, V is the voltage, the electrostatic potential, yes.
Why for gases are charged on the outside.
What's that?
I'm still a little confused why